Well, we'll complete our discussion of mates with mechanical mates. Now, that's a very particular category that applies to mechanisms when there is a programmatic relative motion between two components. What do I mean by programmatic? Well, what I mean is that it doesn't arise naturally from other geometrical constraints. So in SolidWorks, as you create constraints between components, say if you have a collection of bars that are linked in a serial nature, and then you finish them up at the end, the mere act of having declared, for example, concentric constraints at each one of the joints, okay, at each one of the hinges, if you want to think of it that way, will already give you the kinematics of that device, let's say for free. What I say for free, meaning that there's no additional programming, there's no additional action on your part. Okay. Mechanical mates extends that capability in the cases, for example, where there is a gearing ratio between components. Okay, that's one very specific example of mechanical mates. There's also cams, there's also slots, there's also universal joints, and others yet. And we'll take a quick look here at a couple of them. All right. So first of all, the good news is you're getting wonderful kinematic, the power of a kinematic engine in there just through conventional mates. Mechanical mates would allow you to do something really interesting and really fun, like what you would see here with this component. So this is what's called a planetary gear system. Okay, and certain gear mates, gear relations, have been declared between these different parts, so that when I move one, the entire collection is going to move accordingly. So all I'm doing in this particular case, I just grabbed the ring gear, and as I move the ring gear, everything else is moving according to the way it has to. Now, I want to bring to your attention that this is not happening because there's any contact in between the teeth. In fact, if you were to look at this, in there you would find that, in fact, there's no contact anywhere. By which I mean, if I take a front view here and come in, very, very close, okay, you'll see that nothing is contacting anything. And the motion is only happening because certain gear mates have been declared between those different components, and a coherent set of gear mates have been set up, so that everything is turning in the proper direction, therefore giving an impression of a proper mechanical working. But again, rest assured, it's not happening because one body is pushing the other body. That's not what's at play here. Notice too that once those mechanical relations, mechanical assembly mates, have been declared, then it really doesn't matter, which one you turn on first, or which one you attempt to move, by action of your mouse. Okay, any of the components that are connected, will cause motion to occur that is consistent with the mates that have been declared. Okay. Now, if you want to see what those mates look like, you would go here, expand the tree. You see the usual complement of coincident constraints, distance constraints, and there you see some gear mates. Well, let's go now through another example of application of gear mates. What we have here on the screen is a housing that has a worm gear transmission. The red shaft would be the input shaft. This component in here that I'm pointing to would be the output gear, which would in turn be connected to an output shaft. Now, we see no teeth here on either the input shaft on the output or the output shaft, and that's okay. For our purposes, it isn't necessary. In fact, we can very well establish the kinematic relationship between those two items through a mechanical mate. All right, what we're looking at right now is an exploded view. We'll look at what those are later in the course. Yet for right now, let's just collapse the assembly and take a look at what it has in it. Okay, so we'll see that we have a number of components. We have a housing, a round cover. There is an offset shaft in there. We'll call that the input shaft, and then we have out here an output shaft. The worm gear would be the component that's inside in there, and we can see that by bringing or hiding that particular component. Okay, so there's our worm gear, and then finally another cover plate that's up there on top. Okay, in fact, let's go ahead and leave that round cover off so that we see what's going on. All right, so presumably we would have tooth engagement there at the worm gear interface. But what we're interested in doing is declaring a mating relationship between the input shaft and the output shaft. Now, of course, no such relationship exists right now, so I can turn the input shaft in there, and of course, nothing is going to happen to the output shaft. They're entirely independent of one another. Now, what I can do then is come into mates in here. Okay, clear the selections. Go to mechanical mates. And under mechanical mates, I'm going to select a gear mate. Notice that there are quite a few choices in here that, depending on what you need, that they may come in very handy. So keep an eye out for them. For now, we'll just select the gear mate. And for a gear mate, what we're going to do is select two round surfaces, for our purposes here. So we're going to select the round surface for the input shaft, round surface for the output shaft. Okay? And having done that, we're now prompted for a gear ratio, as you can see. So we'll say that we want that ratio to be 10:1. Okay, so generally warm gears, have high ratios. Now, notice that it's being given the quantity in inches, but in this case, this will work out properly as just a generic tooth ratio. In fact, you can see there that teeth and diameter are used interchangeably. So if we now accept the mate and put it through its paces, we'll see that as we turn the input shaft, now there is in fact a connection between them, and the ratio is 10:1. Okay, so it takes 10 turns of the input shaft in order to obtain 1 turn of the output shaft. Now, if we go back and modify that mate or edit the mate, which is of course easy enough to do, just select the mate, edit its properties. We can do things like reverse the direction, so that would mean that now as we turn in this direction, notice that it just turned from counterclockwise to clockwise on the output shaft. Okay, similarly, we can edit that mate to change the gear ratio at any time, so we could reverse it instead of 10:1, well, I guess 1:10, going from output to input. We'll do 10:1 here, and notice now that 10 turns, or rather a single turn of the input shaft, will result in 10 turns of the output shaft. This is not how a warm gear would operate, by the way. Okay, so with this, we've seen the essence of mechanical mates, as usual, a very light touch on the subject, but I think enough to get you started, down that path, to whet your appetite, to look at all that's available, and in particular, to experiment, so that the day that you actually need it, in order to fulfill a particular function, you know that it's there, and then you can quickly refer to a video out of YouTube or perhaps some quick internet search to get the details.